Hi, this is our video for Discrete case study. First of all, I will introduce our group members. So our group members consist of 6 members, which is Taruna Kugan, anak lelaki Arindran, Stephen Rush, anak lelaki James, Mohisha, anak perempuan Satya Kumar, Kirtana, anak perempuan Raja Sakar, Ahmad Fakuladi bin Azri, and Ahmad Naimah Gimi bin Rosdi. Next, for this case study, we are supposed to find a real life problem that can be solved using graph or tree. So, our group decided to choose Dijkstra's algorithm to solve a problem, which is to find the shortest route to reach a destination. We all know that reaching from a place to the destination have so many ways that we can take. But the problem is, which way is the shortest path to reach to our destination? So for that, we choose a random location from Google Map. Referring to this map, we are going to find the shortest path from Sekolah Kebangsaan Felkra Lubuk Sireh to Kedai Kuitiau Sup Thai Ayu. The starting point, Sekolah Kebangsaan Felkra Lubuk Sireh, will be represented as vertex A, and the Kedai Kuitiau Sup Thai Ayu as vertex W. Next, to make the graph, we are using Graph Online. It is very easy to use this graph online. First of all, we need to choose Add Vertex at the top bar to add a vertex. Then we need to do the same things to add the next vertex. So just click it. After that, to connect the vertex, we need to choose Connect Vertex at the top bar. Then we choose the 2 vertex that we want to connect. Then after that, a Add Edge menu will appear. We need to fill the edge weight. There is also an option to set the text above the edge. Then we choose between directed or undirected for the graph. For this graph, we are making the undirected graph. So just click it. And we need to do the same step for all other vertex until we reach our destination. So this is the final result for our graph. In this graph, junction is the vertex. A path is the path connecting between 2 vertex, and weight is the distance between 2 vertex. To use Dijkstra algorithm, there are 3 steps that we must follow. First, we need to find the shortest path available in the graph that is connected to the current vertex. Second, we need to perform relaxation formula. Then lastly, we update the distance of vertex. For the solution, we are using the relaxation formula where du is the distance of u, cuv is the cost from u to v, and dv is the distance of v. The condition for this relaxation formula is the total of current distance of u and cost from u to v must be less than current distance of v so that we can perform relaxation to the connected vertex. Okay, we will start from A. So because we start with vertex A, the distance will be 0. All other junction from B to W will be assumed as infinite. The connected vertex to the vertex A is vertex B and vertex D. So we perform relaxation to vertex B and vertex D because it connected with vertex A. Okay, from vertex A to vertex D, the current distance of A is 0, while the cost from U to V is 70.11 meter, and the current distance of D is infinite. So we use the relaxation formula. It will be if 0 plus 70.11 meter less than infinite, we will update the distance of vertex D. Okay, next we will move to vertex A to vertex B. The current distance of A is 0, while the cost from U to V is 155.45 meter, and the current distance of B is infinite. So we use relaxation formula. If 0 plus 155.45 meter is less than infinite, then we will update the distance of vertex B. Okay, for now, if we find the shortest path among 70.11 meter, 155.45 meter, and infinite for all other remaining vertex, The shortest path is the 70.11 meter. So we will choose vertex D. After we pick vertex D, we will perform relaxation to connect vertex with vertex D, which is vertex H and vertex E. Okay, we will move to vertex D to vertex H. Okay, the current distance of D is 70.11 meter, while the cost from U to V is 206.49 meter, and the current distance of H is infinite. Okay, we use relaxation formula. If 70.11 plus 206.49 meter is less than infinite, then we will update the distance of vertex H. Next, we move from vertex D to vertex E. The current distance of D is 70.11 meter. The cost from U to V is 122.05 meter, and the current distance of E is infinite. So the condition is if 70.11 plus 122.05 meter is smaller than infinite, so we will update the distance of vertex E. So for now, if we find the shortest path among 276.6 meter, 192.16 meter, 155.45 meter, and infinite for all other remaining vertex, the shortest path is 155.45 meter. So we pick vertex B. The vertex connected to B is vertex C. So we will perform relaxation for vertex C. The current distance of B is 155.45 meter, while the cost from U to V is 118.68 meter, and the current distance of C is infinite. So we use the relaxation formula. If 155.45 meter plus 118.68 meter is smaller than infinite, if it is true, then we will update the distance of vertex C. So if we find the shortest path among 276.6 meter, 192.16 meter, 274.13 meter, and infinite for all other remaining vertex, the shortest path is 192.16 meter. So we pick vertex E. The vertex connected to E are vertex C, vertex F, and vertex O. After we pick this vertex E, we must perform relaxation to all the connected vertex. So from vertex E to vertex O, the current distance of E is 192.16 meter. The cost from U to V is 198.12 meter, and the current distance of O is infinite. So if 192.16 plus 198.12 meter is smaller than infinite, which is true, then we will update the distance of vertex O. Then we move from vertex E to vertex C. The current distance of E is 192.16 meter, while the cost from U to V is 224.08 meter, and the current distance of C is 274.13 meter. So we use the relaxation formula. The condition is if 192.16 plus 224.08 meter is smaller than 274.13 meter, so this time the condition is false. So we will not update the distance of vertex C. So we will move from vertex E to vertex F. The current distance of E is 192.16 meter, while the cost from U to V is 114 meter, and the current distance of F is infinite. So we use relaxation formula. The condition is if 192.16 meter plus 114 meter is smaller than infinite, which is true, then we will update the distance of vertex F. So for now, if we find the shortest path among 276.6 meter, 306.16 meter, 274.13 meter, 319.28 meter, and infinite for all other remaining vertex, the shortest path is 274.13 meter. So we will pick vertex C. The vertex connected to vertex C is vertex E and not vertex B, because we already visit vertex B. So we perform relaxation to the connected vertex. Okay, from vertex C to vertex E, The current distance of C is 274.13 meter, while the cost from U to V is 224.08 meter, and the current distance of E is 192.16 meter. So we use the relaxation formula. The condition is if 274.13 meter plus 224.08 meter smaller than 192.16 meter, which is false this time. So we will not update the distance of vertex E. Okay, for now, if we find the shortest path among 276.6 meter, 306.16 meter, 390.28 meter, and infinite for all other remaining vertex, the shortest path is 276.6 meter. So we pick vertex H. The vertex connected to vertex H are vertex G and vertex I, not vertex D because we already visit vertex D. So we will perform relaxation to the connected vertex. We will start from vertex H to vertex I. The current distance of H is 276.6 meter, while the cost from U to V is 393.87 meter, and the current distance of I is infinite. So this is the condition. The condition is true, so we will update the distance of vertex I. Next, from vertex H to vertex G, the current distance of H is 276.6 meter, while the cost from U to V is 113.12 meter, and the current distance of G is infinite. So this is the condition. It is true this time, so we will update the distance of vertex G. For now, if we find the shortest path among 306.16 meter, 390.28 meter, 389.72 meter, 640.47 meter, and infinite for all other remaining vertex, the shortest path is 306.16 meter. So we pick vertex F. The vertex connected to vertex F are G, vertex E, and vertex N. We will perform relaxation to the connected vertex. So we start from F to vertex G. The current distance of F is 306.16 meter, while the cost from U to V is 93.14 meter, and the current distance of G is 389.72 meter. So this is the condition. It is false, so we do not update the distance of vertex G. We move to vertex F to vertex E. The current distance of F is 306.16 meter, while the cost from U to V is 114 meter, and the current distance of E is 192.16 meter. So this is the condition. It is false, so we will not update the distance of vertex E. Next is vertex F to vertex N. So the current distance of F is 306.16 meter, while the cost from U to V is 197.14 meter, and the current distance of N is infinite. So this is the condition. It is true, so we will update the distance of vertex N. If we find the shortest path among 389.72 meter, 640.47 meter, 503.13 meter, 390.28 meter, and infinite for all other remaining vertex, the shortest path is 389.72 meter. So we pick vertex G. The vertex connected to vertex G are vertex L and not vertex F because we already visit vertex F. So we will perform relaxation to vertex L. From vertex G to vertex L, the current distance of G is 389.72 meter, while the cost from U to V is 243.27 meter, and the current distance of L is infinite. So this is the condition. It is true, so we will update the distance of vertex L. Okay, for now, if we find the shortest path among 632.99 meter, 503.13 meter, 640.47 meter, 390.28 meter, and infinite for all other remaining vertex, the shortest path is 390.28 meter. So we pick vertex O. The vertex connected to vertex O are P and vertex N. The vertex connected to vertex O are vertex P and vertex N, but not vertex E because we already visit vertex E. So we will perform relaxation to the connected vertex. From vertex O to vertex N, the current distance of O is 390.28 meter, while the cost from U to V is 110.82 meter, and the current distance of N is 503.3 meter. So this is the condition. It is true. So we will update the distance of vertex N. We move to vertex O to vertex P. So the current distance of O is 390.28 meter, while the cost from U to V is 111.99 meter, and the current distance of P is infinite. So this is the condition using relaxation formula. It is true this time, so we will update the distance of vertex P. For now, if we find the shortest path among 632.99 meter, 501.1 meter, 640.47 meter, 520.27 meter, and infinite for all other remaining vertex, the shortest path is 501.1 meter. So we pick vertex N. The vertex connected to vertex N are vertex S, vertex M, and vertex O, but not vertex F, because we already visit vertex F. So we will perform relaxation to the connected vertex. We start from vertex N to vertex O. The current distance of N is 501.1 meter, while the cost from U to V is 110.82 meter, and the current distance of O is 390.28 meter. So this is the condition. It is false. Next, from vertex N to vertex S, the current distance of N is 501.1 meter, and the cost from U to V is 111.39 meter, while the current distance of S is infinite. So this is the condition. It is true, so we will update the distance of vertex S. We move to vertex N to vertex M. The current distance of N is 501.1 meter. The cost from U to V 263.58 meter, while the current distance of M is infinite. So this is the condition. It is true, so we will update the distance of vertex M. For now, if we find the shortest path among 632.99 meter, 764.68 meter, 640.47 meter, 612.49 meter, 502.27 meter, and infinite for all other remaining vertex, the shortest path is 502.27 meter. So we pick vertex P. The vertex connected to vertex P are vertex Q and vertex S, but not vertex O because we already visit vertex O. So we perform relaxation to the connected vertex. From vertex P to vertex S, the current distance of P is 502.27 meter, while the cost from U to V is 111.98 meter, and the current distance of S is 612.49 meter. So this is the condition. It is false, so we do not update the distance of vertex S. Next, from vertex P to vertex Q, the current distance of P is 502.27 meter, while the cost from U to V is 105.74 meter, and the current distance of Q is infinite. So this is the condition. It is true, so we will update the distance of vertex Q. So for now, if we find the shortest path among 632.99 meter, 764.68 meter, 640.47 meter, 612.49 meter, 608.01 meter, and infinite for all other remaining vertex, the shortest path is 608.01 meter. So we will pick vertex Q. The vertex connected to vertex Q is vertex R, but not vertex P because we already visit vertex P. We will perform relaxation to this connected vertex. From vertex Q to vertex R, the current distance of Q is 608.01 meter, and the cost from U to V is 248.14 meter. The current distance of R is infinite. So this is the condition. It is true, so we will update the distance of vertex R. So for now, if we find the shortest path among 632.99 meter, 764.68 meter, 640.47 meter, 612.49 meter, 608.01 meter, and 856.15 meter, and infinite for all other remaining vertex, the shortest path is 612.49 meter. So we pick vertex S. The vertex connected to vertex S is T, but not vertex P because we already visit vertex P. So we perform relaxation to the connected vertex. From vertex S to vertex T, the current distance of S is 612.49 meter, while the cost from U to V is 120.88 meter, and the current distance of T is infinite. So this is the condition. It is true, so we will update the distance of vertex T. Next, if we find the shortest path among 632.99 meter, 764.68 meter, 640.47 meter, 733.37 meter, 856.15 meter, and infinite for all other remaining vertex, the shortest path is 632.99 meter. So we will pick vertex L. The vertex connected to vertex L are vertex K and vertex M, but not vertex G because we already visit vertex G. So we perform relaxation to the connected vertex. From vertex L to vertex K, the current distance of L is 632.99 meter, while the cost from U to V is 120 meter, and the current distance of K is infinite. So this is the condition. It is true. So we will update the distance of vertex K. Next is from vertex L to vertex M. The current distance of L is 632.99 meter. The cost from U to V is 89.81 meter, while the current distance of M is 764.68 meter. So this is the condition. It is true. So we will update the distance of vertex M. So for now, if we find the shortest path among 722.8 meter, 752.99 meter, 640.47 meter, 733.37 meter, 856.15 meter, and infinite for all other remaining vertex, the shortest path is 640.47 meter. So we pick vertex I. The vertex connected to vertex I is vertex J, but not vertex H because we already visit vertex H. We perform relaxation to the connected vertex. From vertex I to vertex J, the current distance of I is 640.47 meter, while the cost from U to V is 76.36 meter, and the current distance of J is infinite. So this is the condition. It is true, so we will update the distance of vertex J. Next, if we find the shortest path among 722.8 meter, 752.99 meter, 716.83 meter, 733.37 meter, 856.15 meter, and infinite for all other remaining vertex, the shortest path is 716.83 meter. So we pick vertex J. The vertex connected to vertex J is vertex K, but not vertex I, because we already visit vertex I. So we perform relaxation to the connected vertex. From vertex J to vertex K, the current distance of J is 716.83 meter, while the cost from U to V is 230.98 meter, and the current distance of K is 752.99 meter. So this is the condition. It is false, so we will not update the distance of vertex K. So if we find the shortest path among 722.8 meter, 752.99 meter, 733.37 meter, 856.15 meter, and infinite for all other remaining vertex, the shortest path is 722.8 meter. So we pick vertex M. The vertex connected to vertex M is vertex U, but not vertex N and vertex L because we already visit the vertex. So we perform relaxation to the connected vertex. From vertex M to vertex U, the current distance of M is 722.8 meter, while the cost from U to V is 120.27 meter, and the current distance of U is infinite. So this is the condition. It is true this time, so we will update the distance of vertex U. Now, if you find the shortest path among 843.07 meter, 752.99 meter, 733.37 meter, 856.15 meter, and infinite for all other remaining vertex, the shortest path is 733.37 meter. So we will pick vertex connected to vertex T, vertex R and vertex U, but not vertex S because we already visit vertex S. So we perform relaxation to the connected vertex. From vertex T to vertex R, the current distance of T is 733.37 meter. The cost from U to V is 103.63 meter, while the current distance of R 856.15 meter. So this is the condition. It is true, so we will update the distance of vertex R. Next, from vertex T to vertex U, the current distance of T is 733.37 meter, while the cost from U to V is 120.88 meter, and the current distance of U is 843.17 meter. So this is the condition. It is false, so we do not update the distance of vertex U. Now if we find the shortest path among 843.07 meter, 752.99 meter, 837 meter, and infinite for all other remaining vertex, the shortest path is 752.99 meter. So we pick vertex K. The vertex connected to vertex K is vertex V, but not vertex J and vertex L because we already visit them. From vertex K to vertex V, the current distance of K is 752.99 meter, while the cost from U to V is 411.20 meter, and the current distance of V is infinite. So this is the condition. It is true, so we will update the distance of vertex V. So now, if we find the shortest path among 843.07 meter, 1164.19 meter, 837 meter, and infinite for the remaining vertex, the shortest path is 837 meter. So we pick vertex R. The vertex connected to vertex R are not Q and not vertex T, because we already visit vertex Q and vertex T. Now we cannot perform relaxation to the connected vertex. So now, if we find the shortest path among 843.07 meter, 1164.19 meter, and infinite for remaining vertex, the shortest path is 843.07 meter. So we pick vertex U. The vertex connected to vertex U is V, but not vertex T and vertex M because we already visit them. So we perform relaxation to the connected vertex. From vertex U to vertex V, the current distance of U is 843.08 meter, while the cost from U to V is 84.44 meter, and the current distance of V is 1164.19 meter. So this is the condition. It is true, so we will update the distance for vertex V. Next, if we find the shortest path among 927.51 meter and infinite for a remaining vertex, the shortest path is 927.51 meter. So we pick vertex V. The vertex connected to vertex V is vertex W, but not vertex U and vertex K because we already visit them. We perform relaxation to the connected vertex. From vertex V to vertex W, the current distance of V is 927.51 meter, while the cost from U to V is 109.35 meter, and the current distance of W is infinite. So this is the condition. It is true, so we will update the distance of vertex W. So lastly, the remaining vertex, which is W, and the remaining path 1036.86 meter. The shortest distance from vertex A to vertex W is 1036.86 meter. So the path is A, D, H, G, L, M, U, V, and W.